Hello grade 12s and welcome to this video on the table of standard reduction potentials. This is a very important table that you will be making a lot of use of in this section. Very important, you need to make use of table 4a, and I suggest that when you get into your exam, you cross out table 4b immediately. The tables are very similar, but 4b is a flipped around version of 4a. I often find that when learners get into the exams, they become very nervous, very anxious, and then they take readings from 4b and get everything incorrect. So be very careful. We are going to be making use of 4a. Now, this table of standard reduction potentials can be used for many things, one of which is to write down and balance chemical equations for redox reactions. So you may remember those net ionic equations. We are going to be using this table in order to get those equations from now on. Also, those reduction half reactions, oxidation half reactions, we are going to be using this table to obtain those half reactions. Number 2, you can use the table to calculate the EMF of your electrochemical cells. So remember in the previous video, I told you that electrochemical cells include your galvanic cell and your electrolytic cell. The galvanic cell is like a battery. We turn chemical energy into electrical energy, and it therefore has an EMF like any other cell which you would connect in a circuit to make your light bulb shine. So we can use this table to calculate the EMF of our cells. And lastly, we can use it to predict if a redox reaction will take place spontaneously or not. You're going to find that when we are dealing with galvanic cells, they involve spontaneous reactions. Electrolytic cells involve non-spontaneous reactions. In this video, I'm going to be using exercise 7, question 1.1 and 1.2, in order to show you how we do the first bullet point. But I'm also going to show you, well, to some extent, how we know when a reaction is spontaneous and somewhat when it is not spontaneous, but I'm not going to go into too much detail as I don't want to confuse you guys. So our focus here is writing down equations using these tables. So here's a table. I hope that you have yours with you. If you look at this table, you will notice that there are a whole lot of half reactions over here. We have in between the symbol that you would use for a reversible reaction. These reactions are not necessarily reversible in the sense that they won't just happen on their own. It depends on which chemicals you put together. Then it may be spontaneous or non-spontaneous. But the reason why we have these symbols here in the middle is because the forward reaction, when we write it out in that direction, would represent a reduction half reaction. And if we write it out in that direction, we would have the oxidation half reaction. Okay, so that is actually why we have those two arrows there. This table, again, is table 4a. And the table of standard reduction potentials is actually supposed to show you or indicate to you how spontaneous reactions work. So any trends indicated by these arrows and lines on the side is for spontaneous reactions that take place in galvanic cells. Things are going to happen in the opposite direction when it comes to the electrolytic cells, and that's what makes this section so confusing. But don't worry, I'm going to do my best to explain everything to you and to not oversaturate you in this video. So on the left and right hand side, you can see arrows with writing on them. On the left hand side, it says increasing oxidizing ability as you go up. If a substance has a large oxidizing ability, it means that that substance is a very good oxidizing agent. Anything that is a good oxidizing agent will be reduced if it is allowed to behave as that oxidizing agent. So it will be reduced. On the right hand side, it says increasing reducing ability as you go down. So that means that as you go down, we have very good reducing agents. And you guys should know that if something is a reducing agent, it itself will be oxidized. So basically what this means is if you are trying to create for yourself a galvanic cell, you're going to want to choose chemicals at the top as your oxidizing agents, and you're going to want to choose chemicals at the bottom as your reducing agents. That's basically what this means. And if we have a spontaneous reaction, your chemicals at the top would be the reduction half reactions, and those at the bottom would be the oxidation or half the substance that would those at the bottom would be the oxidation half reactions. Okay, hope I haven't confused you just yet. Let's go on to exercise 7. So in exercise 7, we are dealing only with spontaneous reactions. I'm going to explain to you how I know that these are spontaneous reactions. We're going to only do question number 1.1, and question 1.2 will be there just to help reinforce everything. So 1.1 says magnesium ribbon. Magnesium ribbon is Mg solid. It's magnesium that has been put into sheets, thin sheets that look like ribbon. They say it reacts with dilute sulfuric acid. Sulfuric acid is H2SO4. And in the end, we have as a product hydrogen gas being released. Okay, so on the left, my magnesium and my sulfuric acid are my reactants, and one of my products is hydrogen gas. You don't need your table of standard reduction potentials to answer these questions, but I'm going to show you how we can use it anyway. So, in this equation, what you should notice is magnesium is just magnesium. It's an element. It's made up of one type of atom. So that means that its oxidation number is 0. In sulfuric acid, the sulfate ion has a charge of -2 and therefore an oxidation of -2. How do I know that? Because we've learned it off by heart since grade 10. Hydrogen would be +1. Each hydrogen would be +1. That is their oxidation numbers. On the right hand side, hydrogen has the oxidation number of 0 because it's just hydrogen. It's just 2 hydrogen atoms. It means that's an element because it's made up of one type of atom, and therefore its oxidation number is 0. Looking at this, you should realize that our hydrogen goes from an oxidation number of +1 to 0. That means that it has gained electrons to cancel out that positive oxidation number. And if something gains electrons, remember oil rig, oxidation is loss, reduction is gain. So that tells us that our hydrogen has been reduced. Automatically we know that the magnesium therefore would have lost electrons and is therefore oxidized. Alright, now we need to, number 1, write down the oxidation half reaction for this, and number 2, write down the reduction half reaction. We can do that based off of our grade 11 knowledge, but I'm going to show you how to use your table to do so. We are making use of magnesium and hydrogen. So we go up to our table and we look for magnesium and hydrogen. Here is hydrogen and here is magnesium. So remember I told you guys over here, I'll move it down for you. We said that when you write the reduction half reaction, the arrow faces the right, and, well, not faces the right, but when you look at these written down in your table of standard reduction potentials, then the forward reaction is the reduction half reaction and the reverse reaction is the oxidation half reaction. Remember, our hydrogen ions gain electrons to form hydrogen gas. That is the substance being reduced. So that's why the arrow points to the right, or at least we are taking the forward reaction as the reduction half reaction. Then with our magnesium, it starts off as a solid and then goes into its ion form when it loses electrons. So this is our oxidation half reaction. So we take the reverse of that. Before I go and write these answers down, I would like to show you guys another trend that you can identify from this table. If you want to tell if a reaction is spontaneous or not, then number one, what I want you to do is I want you to identify the products in your half reactions. Once you're done doing that, you are going to connect them with a line. When you're done connecting them, you will analyze the gradient of the line that you have drawn. If you find that you have a positive gradient, in other words, the line lies like that, it means that we have a spontaneous reaction. On the other hand, if you have a negative gradient and your line lies this way, it is non-spontaneous. Please go and write this down. Okay, so looking at these substances, this is a spontaneous reaction. Why? My products are hydrogen gas and magnesium ions. When I draw a line to connect the products, I get a positive gradient, and therefore this is a spontaneous reaction. In these problems I'm solving now, we do not deal with a non-spontaneous reaction. So I unfortunately will not show you an example of that, but just for now, take note of how I know that this reaction is spontaneous. Back to writing down our reduction and oxidation half reactions. Even though in this case, you can see the arrows pointing towards the left, we don't write it down like that when we answer the question. We're going to say number one, Mg solid. So we write our reactant on the left is going to form Mg aqueous plus 2 electrons. You must write it out this way. Please don't write it out as it appears there. That is wrong. You're not going to get your marks. Then we write down the reduction half reaction to answer question number 2. So for the reduction half reaction, we have that the H plus, the two H pluses are going to gain 2 electrons, and then they're going to form hydrogen gas. Please do indicate the phases of the different substances. So we're done with that, and notice that I obtained this over here all from my table of standard reduction potentials. Question number 3 says we need to write out the balanced net reaction. So remember, when you are writing down a net reaction, unless they say that you need to show your spectator ions, it's not necessary to do so. So we don't include our spectator ion. And over here, number 1, we make sure that our charges are balanced. They are, we have 2 and 2. So we can sort of pretend that that is not there. Then we have Mg solid, the one reactant plus 2H plus aqueous. The other reactant is going to form Mg2 plus aqueous, that one, plus H2 gas, that one. And that is the balanced net reaction. So net reaction means we don't need to show electrons, don't need to show our spectator ions. Now just for sake, I want to show you how we would show the spectator ion. If our spectator ions were here, then we would say Mg solid plus, instead of 2 hydrogen, it's going to be H2SO4. Is going to go and form, so that is aqueous, is going to go and form Mg, that is bonded to the sulfate ions, plus, okay, so that's aqueous, plus H2 gas. Okay, so that's when we include the spectator ion. But in this case, our spectator ion does not take part in this redox reaction. It just lies around. Okay, so we are done with question 1.1, and we can now go on to question 1.2. And I'm again going to be making use of that table of standard reduction potentials. Here they say steel wool, which contains iron, is added to lead nitrate. So this is lead 2, so that's Pb. Nitrate ions have a charge of -1, so this will be NO3 2, because if this Pb has a charge of 2+, and each of these has a charge of -1, we're going to need 2 of those to get the charge to be 0. Very, very important. And they say that this is going to form Fe2+ ions. Okay, so we have our reactants, and they are going to form one of the products being ions. We need to write down the oxidation half reaction and the reduction half reaction. What is important here is your ion forms a charge of +2. I want us to go up to this table, and I want you to take note of quite a few things. Alright, here is an equation for iron. Here is also an equation for iron. If you look at these two equations, the one involves iron with a charge of 3+. The other involves the iron with a charge of 2+. It's very important to take note of what ions our iron will form in these solutions. And the way you're going to do that is by looking either at the Roman numerals, if they give you Roman numerals like that, or looking at your polyatomic iron and how it bonds to that, or looking at just the products formed. But very important, you need to take note that there's more than one ion here, so you need to choose the correct ion. Okay, so we're going to use the one at the bottom because the product is Fe2+. They say that this is reacting with Pb, that is lead. Here is my lead, and it's Pb2+. So now, remember, we need to write down our oxidation and reduction half reactions. Our lead starts off as Pb2+ and forms to Pb solid. Our iron starts off as iron solid and ends up as Fe2+. Notice that this reaction, what is happening here is according to the trends on this table. The reduction half is at the top, the oxidation half is at the bottom. Remember, I wrote this down in the beginning. So that already tells us that this reaction is spontaneous. But to take things a bit further, to check if it's spontaneous or not, remember we circle our products, which is lead solid and iron ions. And then we draw a line to get to connect these products. We find that the gradient is positive, so we have a spontaneous reaction. Not necessary to know for this problem, but I'm just letting you know so that you learn more and more along the way. So now we need to write down our equations. So the oxidation half reaction, question number 1, we are going to say Fe solid is going to lose electrons to form Fe2+ plus 2 electrons. The reduction half reaction, which we also take from our table, is Pb2+ is going to gain 2 electrons, and then it is going to go and form Pb solid. Let's just make sure that I've written that down correctly. Yes, I have. Okay, so now we have these two. Over here, again, our electrons are balanced. Let's pretend that they were not balanced, just so that I can remind you of how this happens. If the top was 2 and the bottom was 3, we would start off by finding a number that both 2 and 3 can fit into. We'd multiply the top by 3 and then end up with 3, 3, 6. We'd multiply the bottom by 2 and then end up with 2, 6, 2 to balance the electrons, and then we would go on to the next step. So that is what happens when the electrons are not balanced. Just a reminder, that is grade 11 work. but it is done towards the end of the year, so you guys tend to study that a bit less. So now we can go on to question number 3. Our electrons are balanced. We pretend that they are not there, and then we go and write Fe solid plus Pb2 plus aqueous is going to go and form Fe2 plus aqueous plus PbS solid. And ladies and gentlemen, that brings us to the end of question 1.2 and the end of this video. Just to quickly run you guys through everything, basis of this, you can find everything from your table of standard reduction potentials. We use table 4a. If our reaction is spontaneous, the reduction half reaction, it can be found at the top. The oxidation half reaction is found at the bottom. And to check if something is spontaneous or not, we check the gradient of the line that joins their products. Thank you for watching.